This one is, we had separable and first order linear. Which one's this? Separable. Yeah, this is a separable. And the reason it is so called is because we can separate the x's and the y's. So I want the x's, including the x's and dx's, to one side, the dy's and the y's to the other side. So wouldn't that mean multiply both sides by dx and by e to the y? Multiply both sides by, you know what I'm saying? So I have e to the y dy, so I'm going to multiply both sides by e to the y and dx. So that'll get rid of dx on this side, but I'll put e to the y this side. And then 2x squared plus 1 over x dx to this side. And then remember, if we separate them, then we can integrate both sides, which the integral of e to the y dy would be e to the y. And then on this side, any thoughts? How about we do this? Break both of those up, divide both those by x, so that would be 2x plus 1 over x, wouldn't it? And those are just two simple antiderivatives, so we have e to the y equals x squared, because the 2's cancel. And then what's the antiderivative of 1 over x? ln. And sometimes it's ln of absolute value of x, but I don't need the absolute value of x's here. Why? Because I've got x is greater than 0. So I don't have the absolute value case here. And then I also need plus c. Okay? All right? Now the idea when I solve a differential equation is I want to find the y equation that solves it, solution-wise. Actually, it'll be a family of solutions, but how do I solve an e to the y for y? How about we take the ln on both sides? Because won't that cancel out the e base? Yeah, ln of e to the y is just y. So there you go. That's the answer. Yep. That is your answer. Well, if you had the log of a product, you might could clean it up, or if you had, I don't think that one cleans up, so it's just, yeah, that's it. Right, because if you had ln of something times something, you could say that's ln of a plus b, ln of b. I don't have that here. I've got ln of something plus something plus something. So yeah, that's it. Number 11, though, is the other variety. That is not separable. If I tried to separate that, I've just got a big mess. This is a first-order linear differential equation. Now, the first-order linear the preferred format of a first-order linear differential equation is what? Y prime by itself plus some function of x, p of x, times y equals some function of x on the other side. That's our preferred form, right? Remember that? That's not what I got. I need to rearrange some things here, don't I? What's one thing I need to do? Well, one thing, I need the y term on this side, don't I? So make it e to the x, y prime, minus 2 e to the x, y equals 1. First step. Second step is what? What else do I need to do here? Well, first order linear, I like y prime by itself, so I need to get rid of the e to the x. Let's divide both sides by e to the x. So that'll make it y prime minus 2y equals, let's call that e to the minus x. With me so far? So there's my p of x. P of x is negative 2. And my q of x is e to the negative x. Now what do I do with that? That's where yeah. We also are going to do an I of it, an integrating factor, they call it. So that's, I guess, where the I comes from. Remember what I of x was? e to the integral of p of x, yeah. So that's e integral p of x is negative 2. Okay, that's pretty nice. So that's e. Integral of negative 2 is negative 2x. And on these, c will come in at the end, so we're going to choose c to be 0. C will happen later. So anyway, that's I of x. So remember what our solutions are then? That's another formula. It's 1 over I of x. Where are you? Times the integral of I of x q of x. Something like that? Does that ring a bell? Isn't that the solutions? The y equals solutions? I believe so. So in this case, we've got y equals 1 over e to the negative 2x times the integral e to the minus 2x. The q of x comes from right up here. It's e to the minus x dx. So that's y equals e to the minus 2x is just e to the 2x, isn't it? And the integral is e to the minus 3x because we can just combine, you get different things there, but just you got to roll with whatever you got. But in this case, e to the minus 2x times e to the minus x is e to the minus 3x. So that's going to be a nice little integral, isn't it? Use a little u substitution. U equals negative 3x. Du then would be negative 3 dx, or du over negative 3 is dx. So I have y equals e to the 2x integral e to the u times du over negative 3. Hey, that's just a nice integral there. It's e to the 2x times, let's call it negative 1/3. E to the u is e to the u antiderivative. U is, though, negative 3x plus c. And then you just clean this up, multiply that in. Y equals, see, negative 1/3. E to the x times e to the minus 3x. Add those, be e to the minus 2x. And then e to the x times c, or c e to the x. Those are my solutions. And, this is a family of solutions because of the c. C can be any number. So any number for c would satisfy this differential equation. If I plugged in that for y and y prime back in the original equation, that any of those would work. Now, I don't know if I have one on the final, but remember the other component to this was the initial value. If I was given an initial value, y y of 0 equals this, 5, whatever, what would that allow me to do? Find the particular solution, the c value. Oh, 2x. Is that what you're saying? I guess I just didn't want it to be 2x, so I've changed it. But it should have been 2x. All right. So what does that change? That makes it just minus x, yeah. Sorry about that. This will be 2x. Does that look better? Negative 1/3 e to the minus x plus c e to the 2x. Sound better? Okay. No. No. C is just a constant. It doesn't have to. A lot of times we get c over something and we just change it back to a regular constant. But no, that one doesn't. It's just c. Number 12. I think finish this off here. If you have to go, fine, I'll post all this. But the last, I think I just had 3 more, don't I? Parametric and polar. So don't forget about our parametric and polar friends there. Number 12 is the parametric. We graphed them. We found areas and we did different things. Parametric. This one, though, I think it's on the objective sheet, so I'm probably sure we've got one like this or similar to it. Find the equation of the tangent line for a parametric curve at t equals 3. Well, to find the equation of a tangent line, I need the derivative, dy dx. How do I do dy dx for a parametric? Remember? Well, the parameter is t, and so to do dy dx, don't I do the derivative with respect to t of the y? So I do dy dt over dx dt. Yeah, basically, I'm just going to do the derivative of the y over the derivative of the x. Right? Remember that? All right, what's the derivative of the y? The y is 3t square root, or 3t to the 1/2. So the derivative of the y is going to be 1/2 3t to the -1/2 times 3, chain rule. Then the bottom derivative of the x, is that minus x? Okay. So that would be minus t to the 1 to the half, so it would be -1/2 t plus 1 to the -1/2. Derivative of the inside is 1. Good news there is the 1/2s cancel. And what I'm going to do is, these are just going to flip-flop, aren't they? This one's going to go up and that one's going to go down. So it'll be the square root of t plus 1, let's write it this way, over negative the square root of 3, that should be t, 3t. I have an x there, that should be a t. Does that look okay? 3 square root of t plus 1 over negative square root of 3t is the derivative dy dx. Look okay? I do all that right before we go further and get messed up down the line. What does that give me, though? That gives me dy dx. That gives me the slope, right? Derivative is slope. I want the slope at t equals 3, so the slope is going to be, at t equals 3, it's going to be 3 square root of 3 plus 1 divided by negative the square root of 3 times 3. Hey, that's 3 times the square root of 4 over negative square root of 9. That is 6 over negative 3. Hey, that works out. Negative 2. So the slope of my tangent line is negative 2. The equation, y equals mx plus b, how do I get that? Well, m is negative 2. The b I need to figure out. And how do I do that? Well, I don't have x and y specified, but I can figure out x and y, can't I? At t equals 3, at t equals 3, wouldn't x be negative the square root of 3 plus 1? That's negative square root of 4, that's negative 2. And the y at at t equals 3 would be square root of 3 times 3, that's square root of 9, which is 3. So I can figure out b then. Y is 3, b is also, x is negative 2. Hey, that's negative 3 equals 4 plus b. That's negative 7 equals b. So it's negative 2x minus 7, y equals. Would be my tangent line for this particular curve. I think I have one of the objectives too on the final is graph these tangent lines. So be sure you can graph. We haven't looked at the graph of that, but be sure you can graph these parametric. Oh. Right here? It shouldn't be there. Negative 1, would that be better, suit you? (2x minus 1), negative 2x minus 1? All right. If you must, okay, be correct, then, yeah, that's it. All right. All right, last page. 2 more? Just 2 more. Of course, this isn't all stuff, but because we still had done the series and stuff like that, but it's a pretty good reminder for some of these. What about dy dx for a polar curve? Well, for a polar curve, we're kind of going to do it just like we did the parametric. Can I write this sort of in a parametric mode? What is x in polar? If I wanted to convert from polar coordinates to xy coordinates, rectangular coordinates, x equals r cosine theta, yeah. X equals r cosine theta, and y equals r sine theta. Well, in this case, my r is 3 cosine 2 theta. So it'll be 3 cosine 2, plug in that for r. So it'll be 3 cosine 2 theta times cosine theta, and then r 3 cosine 2 theta times sine theta would be the y. That's how I can get dy dx, because now just do the do the y prime over the x prime, basically dy d theta or dx over dx d theta. I guess is the way we really put it. And that's just going to be some product rule. dy d theta, so it would be 3 cosine 2 theta times the derivative of sine, which is cosine, plus the sine times the derivative of 3 cosine 2 theta, which would be, what, negative 3 sine of 2 theta times 2, chain rule. And then the bottom, the dx, product rule, 3 cosine 2 theta times the derivative of cosine would be negative sine. And then the cosine, take times the derivative of 3 cosine 2 theta. Which is the same thing as I got right there. What can I clean that up with? 3 cosine 2 theta, cosine theta, minus 6 sine theta sine 2 theta. And then about the same thing happens down here. Negative 3 cosine 2 theta sine theta minus 6 cosine theta sine of 2 theta. Something like that. So yeah, it's a mess for dy dx. It's not too bad, but it's a long thing. I want to remind you of that. All right, is that okay? Hang with me for one more. Area inside the polar curve, r equals 2 sine theta, but outside, yeah, so finding areas of polar things. Well, let's draw this out. I think I've got it just handy right here. I can change my mode to polar. 2 sine theta, r equals 1, okay. Zoom in a bit. Here's what I got. 2 sine theta looks like this. R equals 1 looks like that. So I want inside 2 sine theta, but outside r equals 1. I want that right there. How do I do that? Well, if I take the area inside from whatever this is to whatever this is, inside the 2 sine theta, then subtract the area right here, subtract that area, right? That's what I'm going to do. How do I do that? Well, area in polar, what is it? Integral What is it? One. Yeah. I think it's just r. Isn't it 1/2? I thought it was just the area inside. 1/2 r squared d theta, isn't it? Now you're making me. I think it's just one. Let me check. Now you got me doubting here myself. Areas, polar. Yeah, it's 1/2 r squared d theta. Yeah. I think you were, that was arc length. You were doing arc length. I just want area. 1/2 r squared d theta. Okay? So I'm just going to take, now for this one, I want inside the 2 sine theta, so it's going to be 1/2 the 2 sine theta squared minus the 1/2 of the 1 squared, which that's going to be nice, isn't it? The only thing then that remains are, what about my limits? It's where they intersect, isn't it? Set them equal, yeah. So 2 sine theta equals 1. Set them equal. That's going to be sine of theta equals 1/2, which what are the thetas there? Be pi over 6, and then over here would be 5 pi over 6, wouldn't it? 5 pi over 6. So those are going to be my limits. All right, so that's going to be 1/2 of 4 sine squared, minus 1/2. So that's going to be 2 sine squared. What am I going to do with that? Well, that's the old double angle again. So I have 2 times the sine squared is 1/2 minus the 1/2 cosine 2 theta. So that's going to be 1, 2 times that, minus 1 cosine 2 theta, minus 1/2. Well, I can combine the, let's go ahead and combine the 1 minus 1/2. That's just going to be 1/2 minus cosine 2 theta. Well, 1/2 antiderivative is 1/2 theta, minus cosine 2 theta, well, that's just a little u substitution. So it's going to be 1/2. Antiderivative of cosine would be sine of u, but that's 2 theta. And so I want to go, don't do it. So I want to go there from pi over 6 to 5 pi over 6. So I get 1/2 5 pi over 6 minus 1/2 sine of pi over 3. So multiply that by 2. Minus the 1/2 pi over 6 minus 1/2 sine of pi over 6 times 2, which would be pi over 3. So it's 5 pi over 12 minus 1/2 sine of pi over 3, 60, square root of 3 over 2. 5 pi over 3? Okay, if you want to. 5 pi over 3, which that's still square root of 3 over 2. No. That's going to be actually, is that a negative? That's going to put it in quadrant 4. So that's a negative. Thank you. All right, then minus, that would be pi over 12. 5 pi over, okay, so that's my square root of 3 over 2. So that would be plus, okay, so 4 pi over 12. That would be plus square root of 3 over 4. That would be plus square root of 3 over 4, so that's 2 square roots of 3 over 4, which is pi over 3 plus square root of 3 over 2. Which I'm not really trusting at this point, but I think it's right. Anybody see anything wrong with that? If there is, you're not going to tell me, huh? Okay. Oh, she got away before I could give her everything. Okay, so let me get this to you real quick here. See if I can work this up. Okay, the other thing to give you, so 12 o'clock, Wednesday. I'll be around here Monday. I should be testing Calc 1 Monday. So, we're not meeting class, but if you wanted to bring some questions to me, that's fine. Notice on the bottom, oh, wait. I'm giving you the wrong ones. I think I gave you the right one. The bottom has, yes, the bottom has some review problems out of the book. So turn those in Wednesday with the final. 6 points. Okay. Now she has 7th edition. I think so. Yeah. But those they have the specific objectives. And we did most of these, some of these, but we didn't do all of these. Like I said, partial integrate